Okay, chapter number 5, again I/O. We are talking about the aspects of I/O software. Yesterday we talked about this layering of the I/O software. We said that at the bottom we have the interrupt handlers. Interrupt handlers are not that, I mean, the number of lines for interrupt handlers are not that much. Well, the number of interrupts that can happen, the types of the interrupts are not that much. So it is not lots of code for the lower parts, but they are of course critical. They have to be in the kernel mode. On top of it, we have the device drivers, and let's talk about the device drivers. I think we talked about the interrupts many times. I am not going to talk about it again. So when the interrupt happens, there are things that hardware does, okay, and there are also things that the software does after that, and the software part, of course, belongs to the operating system. So let's talk about this device drivers. Device drivers are of course they are software, okay. Okay, device drivers are the software. We know that, okay, and they deal with the corresponding hardware. Okay, for example, we have a device driver that deals with the CD-ROM controller. It's the CD-ROM driver. The same thing is for the if I have a specialized camera connected to my system, it is a camera driver, and etc. Of course, I mean, this is a logical picture. They all are connected. These controllers are connected to the system bus, and of course our drivers, their code are in the memory, and they work that way. But this is again a logical representation of the whole thing. Okay, so the device drivers, as I said before, for each I/O device we have a controller. Okay, that's an electronic device, and that electronic device needs some kind of a software to control it or drive it. It's called the device driver, and usually if this is a CD-ROM device, this is a camera, this is a printer, whoever produced these devices, they write their own device drivers too. Okay, so they sell their devices with the device drivers. Whenever you install a new device to your computer, you install a device driver with it, and it comes from the manufacturer of the device. Okay. Sometimes these device drivers are really simple, sometimes they are not. For example, most of the devices that we use for the maybe last 10-15 years are USB devices. That's why the device driver for the USBs has to be complicated, because they can handle all kinds of stuff, like the hard drives or the system mouse and etc. And very different kinds of devices are connected to that device. Okay, I think I'm using the wrong set of slides, but I think it's okay. Let me clear this out, because this is not the yesterday's slide set, right? Is it? I don't remember. I marked these. Let me find my. Yeah, this is the thing. Yeah, okay, so this is the correct one. Okay, so device drivers, as I said, is part of the operating system most of the time, not all the time, but most of the time. So this is like this is my hardware part, and this is my software part, and this is my software part again, but this is operating system, this is hardware, these are the user programs. Okay, so the device drivers are actually a part of the operating system most of the time. So whatever you get, whatever you buy from the manufacturer of your device, the software part of it becomes your operating system most of the time. There are exceptions like this system, microkernel system. We talked about this microkernel system Minix. Minix says that I am going to keep my kernel very, very small. Only like 10,000 lines of code will run in the pre-revision mode. Rest of the operating system will run in the user mode. Okay, so they don't have any privileges to change the memory map table. Okay, they cannot program MMU, they cannot program DMA, they cannot program the interrupt controls and etc. So they are not part of the operating system in the kernel mode. So the Minix says that's why the drivers, I/O drivers, are not part of the kernel of the operating system. They will run outside of the kernel. So remember, these device drivers, okay, they need to modify those special registers inside the controllers. Remember those controller registers? And to modify those controller registers, you need to be in the kernel mode. But since for the Minix, they are running in the user mode, there is a problem. So the problem will be solved by these drivers are asking the kernel to do something for them. So they need to make system calls lots of time. Okay, so they are making lots of system calls. They ask the kernel to modify that register and do that and do this and etc. So that means that it is context switching, and context switching is expensive. That's the downside of the microkernel operating system. Lots of kernel calls, system calls, lots of context switching. So they have to be optimized accordingly. Okay. So we already talked about this. Now the time came and we talked about this in terms of device drivers. Okay. For the other operating systems like Windows and Linux, device drivers are parts of the operating system, and they are the major, maybe the most common source of the system crashes. Okay, if Windows crashes, okay, it crashes mostly because of the device drivers some other company wrote. It is not the Microsoft's fault that it is crashing, at least what they say. Okay, because as I said before, device driver becomes part of the operating system, and that software can do whatever it wants. And if it's a buggy device driver, then that it may cause a crash, and that crash will take down the whole operating system. Of course, the operating system has to be designed carefully, and it has to be designed in a way that it doesn't crash with these kind of problems. But anyway, that's a known problem. Okay. So most operating systems, they say that if you are going to be a device driver for my operating system, you have to follow some rules. Okay, and they list these rules for types of the devices. For example, block drivers. Remember the block devices? They communicate with the rest of the system in terms of blocks. You give me 5 blocks of data, and it gives you 5 blocks of data, like the disks and CD-ROMs. And at the other end, we have the character drivers, like the mouse and keyboard and etc. Okay, so you define set of rules for these kind of drivers. Whoever is writing the device driver they will follow the rules. Otherwise, they will follow the rules. Otherwise, their device driver won't be able to connect to the system. It will not be installed. Okay? So, these are some information about the device drivers. As we said before, operating systems are very complicated, we said right at the beginning of the semester. And for some systems, we are talking about more than 100 million lines of code. Most of that code comes from this I/O stuff. Okay, I/O stuff and file systems are very diverse, and you need to deal with lots of problems, lots of different devices. That's why you have lots of code for them. The scheduling, memory management, and some basic file systems are not that difficult. But what makes this operating system more complicated is you need to deal with lots of technologies, different CPUs, different memories, stuff, different architectures, and etc. Okay, so we talked about device-independent I/O software. Again, we are talking about the software aspects of the I/O. We need to be device-independent, and when you are becoming device-independent, you need to look at these titles. For example, the buffering has to be done in a device-independent way. Okay, device-independent uniform interfacing with device drivers, error reporting. Okay, block sizes and etc. Let's look at these titles one by one. As I said before, operating systems usually define their standards for the device drivers. They say that I am the operating system. If you are going to be this driver, then you need to have this interface. If you are going to be a USB disk driver, you have to be this interface or this interface. So of course, we like this kind of interfaces because whatever you are the same thing. Okay. For some operating systems, they define lots of other standards. For example, for the USB, they define this. For the SCSE, they define this. For the SATA, they define this kind of an interface. Of course, we prefer this kind of an interface because for the operating system, it is easy to comply with the rules. There are less possibilities of having a bug with the operating system, etc. Of course, object-oriented programming, like you write a base class, abstract base class named driver, okay? It has lots of pure virtual functions, okay? And when you write your, for example, SATA driver, for this one, you derive this from this base class, so you have to implement all those pure virtual functions one by one. And without implementing all of these, you don't become a concrete class, and without becoming a concrete class, you cannot install yourself to the operating system, because operating system needs a driver. Okay, it needs a driver software. I'm not saying that it has to be in this way in C++ or in some object-oriented programming language, but that's the idea. Most of the time, we write our device drivers in C. C++ is okay too. Even if you are doing this in C, so what you need to do is you define lots of function pointers and provide those function pointers to the operating system, saying that operating system says that if you are going to be a device driver for block device driver, okay, you need to fill in this table. This table is a function pointer table. There is a function open file. There is a function for close file. There is a function for seek. Okay, so give me these function pointers. Their parameters are fixed. Once you give me these function pointers, you become a driver. Well, this is basically the same as extending a class or deriving a class. from a base class, because you are providing the implementations for those pure virtual functions. An operating system calls these function pointers whenever the time comes. So writing a device driver is something like that. If your table is always the same type, okay, if your table is always the same type, then you are using this structure, okay, uniform interfacing. If your table structure changes from driver to driver for the operating system, then you are not using a standard driver interface. Okay, that's the meaning of these slides. Okay, so let's move on. Uniform interfacing for the device drivers again. As I said before, for different devices, operating system says that you are going to give me these functions as function pointers, and I will take them and I will call them whenever it is needed, and it is held as a table of pointers. Okay, and in Unix we are doing exactly the same thing. There is a dev directory. Okay, remember Unix structure. How should I? Yeah. At the root, we have the user directory, we have the libraries directory, we have the mount directory, and we have the devices directory. Okay. Under the devices directory, okay, we have the device drivers for each different type of device. I don't have a Unix system on this computer. This is just a stupid simulation of the Unix. Okay, but if you go to that directory in a real system, you will see your device drivers for your desks, for your CD-ROMs, for your keyboard, for your terminals, and etc. Okay, these device driver. Okay, these are the files. Okay, these are some files. Okay. These files, they point to an inode, and those are special inodes. Inside those inodes, you have two things. One is a major number. Major number means that it's the device driver address. Okay, so for this device, I am going to use the device driver number 5. For example, number 5 is a block device driver, and there is a second number. It is the minor number. Minor number is the copy number of that device. You may have more than one disk drive connected to your system. So they are all using the same device driver. Their major numbers are the same, but their minor numbers are ordered from 0 to some number. Okay, that's how the Unix is structured. Even today, we are using the same structure. Okay, so again, it changes from system to system widely. The operating system approaches are very different. At the very far end, there is Minix. Minix says that device drivers are not part of the operating system. Whenever they need to do something privileged, changing the DMA, programming the DMA chip, handling the interrupts, and etc., you need to ask the kernel to do that. That's why lots of context switching. For the other operating systems like Windows, everything is part of the operating system, so they can do mostly they are free to do whatever they want, and there is a risk of crashing the whole system. Okay, so go back to that. Okay, uniform interfacing of the device drivers. We talked about it. Let's talk about buffering. We talked about this before. I think I have shown you this one before. Buffering is important. It's a technique that we use lots of times, and at the one end, no buffer communication with the devices. Okay, no buffer communication with the devices. It doesn't have to be a single directional communication, well, multiple directional communication. Without using any buffer, if you like to communicate with a device, you tell the device that, okay, here is your character, just print this character for me. Okay, whenever it prints, okay, it says I printed it and I'm coming back, give me another character. So that's very inefficient, because you have to do this one by one, and you have to do this communication through the kernel. That means a system call. So every time you need to print a single character, or every time you need to read a single byte of data from your modem, you need to communicate with the kernel. That's expensive, okay? We don't like it. So the idea is, why don't I keep all of my data, okay, in a buffer? I am going to send my data when it reaches one kilobytes of length. When this data is, let's say, 1 kilobyte long, then I ask the operating system to send it. Or maybe the operating system is going to tell me that, okay, your new 1 kilobyte of data is ready, just take it. So instead of doing this 1,000 times kernel call, okay, you do it just once, so that it makes things lots of more convenient, more efficient. Okay, keep your data in a buffer. Okay, collect it there. When the size is enough, then just send it to your data. We do the exactly same thing. Remember, with the our printf statements. If you are printing your stuff character by character, you don't see them immediately on your screen. They come on your screen after a while, after the whole buffer is full. Okay, or if you like, maybe you can say flush the buffer. In that case, you directly communicate with the operating system to print whatever you are printing to the screen. Okay, so this is the buffering. But we made the things a little bit efficient, but there is a problem with this approach. The problem is this. Let's say you ask for the modem to give you 5 kilobytes of data or 10 kilobytes of data. Okay, so you ask the operating system, I am waiting for the data, and the operating system blocked you, and you are waiting for the data. Modem has to connect to the internet and get the data from there, so it takes some time. In the meanwhile, operating system decided that your pages are not being used, your memory pages are not being used, and it paged out your buffer space. Okay, and operating system needs that buffer space, but the memory manager paged out your pages that contains the buffer. That's a problem. Okay, we need to solve this problem. It happens a lot, and this is just one of the problems that can happen with the user memory. Okay, so that's why they say that let's keep this buffer in my kernel space. Okay, keep the buffer in my kernel space. Since the buffer is in the kernel space, there is no problem of paging in the out and in, because everybody is using that space, and I can do my communication between the device using this buffer space. Of course, I have to keep this buffer too. Why? Because otherwise I need to communicate with the kernel in a byte by byte basis and etc., which I don't like. So usually our picture is like this. There is a buffer at the kernel that's used for the communication between the modem and the kernel, and there is a separate buffer at the user space. Okay, of course, depending on how many processes you have that uses the modem, each process is going to keep a separate buffer for it. Okay, so that there might be many buffer spaces that does the communication with the modem. An issue that is common emerges here. Okay, The thing is that, let's say modem is loading lots of data. Okay, modem is loading lots of data. When the data is ready, let's like 1 kilobyte length of data, operating system unblocks the process that needs the data. While I am doing this copying, if the modem needs this buffer space for some other data, then that's going to be a problem. Then we have this solution, double buffering. Okay, in double buffering, one of the buffers are used for communicating with the user spaces, user programs. The other buffer is for loading the new data. Okay, it's called double buffering, and usually this is the case with I/O devices, double buffered. Okay, so we need lots of buffer space, as you see. When it comes to networking, your buffer need for the buffer will be a lot more. I'm going to show you the picture in a few minutes. But that's the way it is. We use lots of buffer spaces, extra buffer spaces. You may think that it is kind of waste of memory, but it is designed this way. It makes things easy, it makes things more efficient. And usually you are going to see this problem, all the time. There is a trade-off between the memory usage and the CPU efficiency. Usually you can find solutions that will make your CPU more efficient, if you use more memory. Okay. If you are trying to use less memory and more efficient CPU, that solution is kind of difficult to come by. But you can trade the memory usage with the CPU efficiency. Good. Okay. So this is all about the buffering that the book tells us. Okay. Let me continue then. Some people say that why don't we use circular buffers? I mean, why are we using the double buffer? Because this one this one is busy. I am transferring the data from this buffer to the user space. Okay. While I am transferring the data from between the kernel and user space, I am storing my new data in here. Why don't you use a circular buffer? Remember what the circular buffer is? Something like this. Okay, like the circle, like the clock algorithm, right? So I put my data in here. With the circular buffer, you have the in part and you have the out part, right? Okay, so whatever is going to be in will be put in here, then there, then there, then there. If I am reading out from this one, I am reading from here, then this one, then this one, then this one. So I can use the same buffer to read in, to put in my data and to read out my data. If the buffer is large enough, I can handle this at the same time. I don't have to keep two separate buffers for double buffering. Instead of double buffering, a large buffer but a circular buffer. Okay. So circular buffer, the story behind it is this. As I said before, buffering is nice, but usually we overdo it. When it comes to networking, this is the situation actually. Okay, there is a buffer at the user space. Kernel keeps a buffer, usually a double buffer or circular buffer. Our network controller, remember our device controller. Okay, controller has a buffer in that too. Let's say this is a network card and it's controller. And while this data is communicated, it's in a special buffer. You may think it that way too. And at the other end, we have the controller, kernel, and see, I have 6-7 copies of the same data being kept at somewhere in my overall system. Okay. So we are not saying that let's eliminate this. Why are we doing this? Just to be more efficient. Otherwise, I have to do lots of kernel calls, or I have to be very slow between this end to that end. I mean, I like to send this data to this end. So if I send it by character, that data, that will solve the whole buffering problem. I don't need anything, but that's going to be very slow. I don't like it. Okay, just to keep things more efficient and fast, we use buffering. We trade off our memory space for the speed. Okay, another, remember this one, interfacing buffer error reporting. Okay, let's look at this case, error reporting. Okay, errors will happen. Okay, and errors depend on the device that you are using. Somebody has to make sure that no two process can use the same printed at the same time. The printers are not shared simply. They are not shared. They cannot be shared. Okay, I can't say the same thing for the hard drives or the network drives. They can be shared in time shared, but printers cannot. So somebody has to make sure that this is not happening. So what I'm saying is that there are special problems for each of them. Okay, the connection problems happen for the network drives, but they don't usually happen for the hard drives, for example. Okay, so errors has to be handled. They have to be handled. Different types of error for different types of devices. Bad sectors is something that happens a lot for the hard drives. They are built that way. Bad sectors has to happen. Okay. Bad sectors will happen for the SSDs, but their bad sector frequency is a little bit different, and the reasons are a little bit different than the others. Somebody has to handle all of that stuff. Usually, we don't like to reflect these problems to the end user. You don't want to say to the end user that there is a bad sector in this hard drive, okay, I am going to abort whatever you are doing. No, we don't want to do that, because if the bad sectors are part of life for the operating system, for the hard drives, if you see a bad sector, then you fix it. How do you fix a bad sector? You mark it as a bad sector, and you never use that sector again, okay? So you use some other sector, and the user doesn't know what's happening. All he sees is that the process is taking a little bit longer because there is a sector replacement being happening, and etc. Okay. Errors has to be allocated this way. This notion of block size. Let's look at this one. This is not an error, but usually with the I/O stuff we do it that way. Okay. Let me show you. No, I think I'm going to talk about it later. When we communicate with our hard drives, we communicate in terms of block sizes. Okay, we say that give me 5 blocks of data. Okay, but as we have seen many times on hard drives, our minimum data unit is the sector. Sector is something different from the block sizes. So somebody has to do this translation for us. Our sector sizes don't have to correspond with the block sizes. Somebody has to do this translation for us. So it is up to the device independent software to hide this fact and to do this translation for us. Okay. Okay, let me move on. You already know this picture. Okay. Hardware are interrupts, device drivers, device independent software, and these are the user processes. And usually this part is definitely within the operating system. Sometimes we keep this part outside the operating system. Remember the mechanisms versus the policy. Policy has the main algorithms in it. Mechanism is the hands of the algorithm. Of course, mechanisms has to be privileged to change the tables and etc. Okay, this is what happens when we do the I/O related software stuff. User process asks something, make I/O call, format I/O, spooling, and etc. Okay, device independent software. It is used for naming your files, protection, blocking, etc. Device drivers, of course, they know their controllers. Okay, they can go into the controller and change their device register, check status. Interrupt handlers, of course, whenever something happens with the device, these interrupt controls are called, and the real hardware performs the I/O operation. So it is layered. I ask you, then you ask this, then you ask this, and it comes back again. Did you see this? This part? So this is a longer arrow. Okay? We don't have a structure like this. There is an arrow here and there is another arrow there, right? We don't have it. Do you know why? Can you guess why? It's just one big arrow. That means that device drivers, they don't talk to interrupt handlers when they are trying to do something with the hardware. But the opposite way, device drivers, they get their data from the interrupt handlers. Yeah, the question is, why is the arrow around the interrupt handler longer than the others? Yes?
Because device drivers are the part of the kernel mode, so it needs to reach the hardware itself.
But this is a layered structure. How come I am not directly talking to the device drivers, but talking to the interrupt handlers in that case?
Because when the hardware is IO operation is done, then it has to inform the device driver that it is over. So it writes to the interrupt handler first. Then
So why don't we do just the opposite when we are communicating with the hardware in the other way? So why are we skipping the interrupt handlers in the other direction?
Maybe hardware doesn't have interrupt controller system.
Well, maybe, but I'm asking the reason why.
Because each hardware is not compatible with each operating system.
So how does it work then?
Operating systems try to optimize themselves to the hardware, not hardware operating system.
Then just get rid of these interrupt handlers altogether and handle it that way.
It's maybe device independent, so it doesn't have to discern between different. There are no handlers. It's the same.
I don't understand what you say it louder.
It is the same for every device driver, the communication with the hardware, because.
So I am asking the reason why.
Because we are using device independent I/O.
Well, the answer is actually not that difficult. You don't talk to interrupt handlers. Interrupt handlers are, as the name implies, their only function is to handle the interrupts. Okay? Whenever an interrupt happens, this interrupt handler handles it. And interrupts are caused by the hardware, right? Interrupts are caused by the hardware. Your device driver doesn't cause an interrupt. It just knows how to communicate with the hardware directly. Well, you can say that, well, how come I need the interrupt handlers? Well, actually, you don't need the interrupt handlers. If you are going to do the polling, right? Remember polling? You just keep checking if that register is ready. Remember that programmed I/O with the printers? Just your device driver keeps checking if the printer is ready. If it is ready, then it sends another character. If your solution is like this, then you don't need the interrupt handlers. Your device driver can directly access to the hardware, but that would be too inefficient. We don't like it. So the task of the interrupt handler is just one way. If something happens with the hardware, just let me know. Okay. Otherwise, when I am running, I am going this direction. I am going this direction. I will control the hardware directly. Okay. This layer is kind of a special layer, so it works just one way. Okay, it works just one way. Device drivers, they don't need the interrupt handlers if you are going to do the polling, but nobody does polling nowadays. It is too inefficient. The picture is not the same here. I cannot directly talk to the hardware with the device independent software. As the name implies, device independent software doesn't know anything about the device control registers. Okay, it just thinks that it works on a block device. Okay, and that's it. So that's why I cannot have a long arrow there. Okay, good. So this is the user space I/O software. Okay, let me move on. Okay. So when we are following this picture, okay, most of the I/O is done by the kernel, and some work needs to be done by the user space. In user space, I do some stuff like remember our printf function. When you call the printf function, printf means formatted printing, right? Print formatted. Formatting done in the user space in the I/O libraries, not in the kernel mode. So what is formatting? Formatting is, okay, I'm going to give you 5 integers and 2 strings. You format them nicely, and you give me, and you produce a nice string that will be printed. That formatting, okay, will be done at the user space. Other than that, most of the I/O work done by the kernel. Okay, most of the work is done by the kernel. We talked about this printer spooling. There is a special process. There is a special process that keeps running. It is called printer spooling. Okay, it's a special daemon. Just sleeps, and whenever you need to print something, you just communicate with this. You communicate with this special process. Tell this process that you need to print a file. So it's kind of a typical producer-consumer thing. Consumer is the printer spooler, okay, and you have many producers, and there is a common buffer in here. So your processes, they put their files to be printed in this special buffer, and of course there might be a race condition. You prevent it in a way. And this one, whenever the data is ready, wakes up and does the printing. Of course, this one doesn't do the printing automatically. It is connected to the. It asks the printing from the kernel. Okay, and the kernel operating system recognizes this as a printer spooling. It accepts print. It accepts print requests only from this process. So it's a special process. It's called the spooler. It's a daemon. Okay. Good. So typical producer-consumer kind of stuff. And if you have many printers connected, you might have many printer spoolers, many consumers. Okay. So let's move on to remember what we said at the beginning of the chapter. We said that we are going to do this. We are going to look at, okay, principles of I/O hardware. We did that. Then principles of software, like the buffering and the layering and the and other stuff, and we did that too. And now we are going to look at the individual I/O devices, and we are going to start with the secondary storage, or the most popular one is the magnetic disks. Okay, so this is a picture. It's an old picture, but this is an old picture about the even older drives, magnetic disks. This is 1984, and 30 years later, this is 2015 maybe. Okay, so this is an older hard disk. This is a floppy disk. If you remember, maybe you have seen floppy disk somewhere. I have one on my wall in my office. So it's a very simple. It's not hard disk. It's, as the name implies, a floppy disk. Okay, it's very simple. It has just two. It has that one platter. Okay, one platter. Number of cylinders is just 40. Since you have a one platter, there is only the upside and the bottom side of the platter. So there are just 2 tracks per cylinder, and for each track I have 9 sectors. So this is my floppy disk, and these are my tracks. there is one upper track, and this is the up part, and this is the down part of it. Just 2 tracks per cylinder, and each track is divided into 9 sectors, like this: 1, 2, 3, 4, 5, 6, 7, 8. What happened? How many do I have? Well, don't count it. This is 9, right? Okay. So we have 9 sectors in it. Okay. And sectors per disk is, we can calculate it actually. It has to be 40 times 2 times 9. Okay. So there are a total of 720 sectors. If I have 512 bytes per sector, just multiply these two and you should get 360 kilobytes of total data. Okay, so that's the structure of the disk in 1984. I am not saying that this was the state-of-the-art magnetic disk at those days, but this was the common one for the personal computers. Okay, the seek time is, okay, 6 milliseconds. What is the seek time? If this is my disk and if this is my read-write head, remember read-write head moves like this way or that way. Okay, from one track to another track here, it takes 6 milliseconds to move my head. Okay, and the average seek time is, it is not adjacent tracks anymore. On the average, moving from one location, from let's say one location to another location, on the average takes, okay, 77 milliseconds. The whole rotation time is 200 milliseconds. So the spins 200, the full rotation is done in 200 milliseconds. And the time to transfer one sector, okay, well, I mean, how do you calculate this to 22 milliseconds here? How did you, I mean, if I don't give you this 22 milliseconds, you can calculate it. How do you do that? If I give you all of this data and I didn't give you this 22 milliseconds, you can calculate it. I give you the rotation time, full rotation, right? I give you the sectors per track. So what are you going to do? You are going to divide 200 by what? 9, right? So if you divide 200 by 9, that will give you the time to read a sector. Okay, time to transfer one sector is 22 milliseconds. So maybe it's an interesting thing. I didn't have to give you this number, right? I didn't have to give you this number, and I didn't have to give you this number. Okay, these are all can be calculated from the others. 30 years later, okay, for this hard drive, maybe half a price of the original floppy. Number of cylinders is 36,000, not 40. Yeah, so I have 36,000 concentric rings. Okay, tracks per cylinder is 255. What does that mean? Tracks per cylinder 255. How could this happen? What does that mean? 255. That means what? It has 128. It has 128 platters. Yeah, that's lots of platters, right? Remember, our disks are formed like that. Okay, this is one platter, and this is another platter, another platter, another platter, and there is a spindle, and it turns around it, right? Rotates around this. So 255 tracks per cylinder. That's a lot. Sectors per track is 63, but it says average. What do you mean by average? Remember, for the IBM floppy drive, if this is my disk, if these are my tracks, I am dividing this into 9. Okay, there are 9 sectors in it. Doesn't matter where I am on the disk, all the tracks have 9 sectors in it. This one says that on the average you have 63 sectors per track, but it says on the average. Yeah?
Inner side of the cylinder, the diameter is smaller.
Yeah, exactly. Yeah, I mean, IBM floppy drive says that, okay, it says that doesn't matter where you are, okay, our tracks are always divided like this. Okay, so this track and this track has same number of sectors, but this Western Digital hard drive says that no, I am going to use smaller number of sectors for the inner tracks. For the outer tracks, I have larger sectors. Okay, and sectors per disk is this. So what do I do with this one? Sectors per disk, 63 on the average. Okay, no, well, yeah, 63 times times the number of cylinders and number of tracks. If you multiply all of these, and you will get this number. And bytes per sector is the same. Okay, so this number did not improve. This number did not improve because we made our sectors a lot shorter. Okay, it is a lot shorter, and our disk capacities, we are talking about 300 gigabytes now. Okay, we are talking about orders of gigabytes. Seek time improved like maybe 10 times, from 6 milliseconds to 0.7 milliseconds. Average seek time is a lot better. Okay, it is like 20 times faster. Maybe rotation time is from 200 milliseconds. 200 milliseconds means that, okay, in a second we have 5 rotations, right? 5 rotations per second. We are talking about 6 milliseconds rotation time. Okay, and the time to transfer one sector, again, very fast, because I am rotating very fast, and my sector sizes are very small, 1.4 microseconds. So lots of developments in here, but if you think about it, most of the developments come from the number of cylinders. So we are using the same magnetic surface. Its physical structure, chemical structure is a lot improved. Okay, instead of putting like 40 cylinders in it, we are putting more than 35,000 cylinders in it. So the density of the data is a lot better. Of course, mechanically we are doing maybe 10 times, maybe 20 times better, but the most development comes from the density of the surface structure. Okay, and I think the similar stuff happened from 2015 to 2020. I mean, nowadays we are not talking about, for the common hard drives, we are talking about a few terabytes of data, and again, you are not going to see many more. You are not going to see much better seek times, average seek times, or the rotation times than these. The improvement will come from the density of your data. Okay, directly from the book. Okay, I think I will stop at this point, and I will come back to this one after the break if you don't have any questions. Any questions? Then let's be here around 44?
Can I ask you a question? Bytes per sector stay same.
What?
Bytes per sector.
Bytes?
Bytes per sector.
Bytes per sector? Yeah, it's the same.
After 30 years, why is the same?
Because you don't want to change your sector size because file systems uses it. but your sectors are very. It used to be 4 sectors here. Now I have what? How many sectors? 250, no, 63. So our new sector size is much smaller, right? So I am putting that 512 in a much smaller place. So there is an improvement there. Hayır.
Hocam imza kağıdında benim yerime birisi dün imza atmış galiba üstünde karalamış sonra haberiniz var.
Evet söyledi bana dün yapmış.
Hastaydım istedik geldim.
Geçmiş olsun ya. Bu sınıfa hiç artık şey yapmıyorum ben ya.
Ama ikinci derste kalıyorum ben.
Tamam,
Derslerim
güzel.
için kalıyorum.
Zaten ben de sizin için gönderdim.
O zaman ikinci ders aldın yoklamayı. Hiçbirinden kalmam yani.
Vallahi teşekkür ederim. Gel bir sonraki derste sen anlat burayı da. Ben de kurtulayım bundan.
Öyle demek istemedim, kusura bakma.
Yok anlatıyorsan böyle güzel fikirlerin varsa söyle buna. Her ders yoklamalıyım öyle mi?
Yemeği nerede yediniz ya? Yemeği nerede yediniz?
Ben bir yerlere geçiyorum.
Yemeği sezdiniz mi?
Dışarıda çok güneş var. Hava serin, daha serin ama daha çok güneş var. Daha iyi. Ha? Evet, dışarıda daha fazla güneş var. Nasıl güneş var?
Abi bu sen zaman. Bu bahane değil.
Şu anda güneş istemiyor. İki sayfa.
2 sayfa.
Yapmış şimdi vereyim diyor. Boş boşuna gaza getirip. Evet.
Ben ilk kez program yapacağım için kimliğimi de ilk kez yaptım. Ama test kimliğimi. O da onun için herhalde böyle. Kazan bir konuşmamıştı. Ben teşekkürler dedim. Söyledi ki memnuniyet anketine yazar mısın dedi. Tabii dedim. Telefonu kapatmadım. Memnuniyet anketi gelecek diye. Müşteri geldi dedim. Mehmet de telefonu kapatmayacak mısınız dedi kadın.
Seni yankıp geldi.
Ben öyle dedim. Siteden yapacaksın. O da bekliyor işte. Yani yasak onu kapattığınızı.
Şaka böyle ne yaptı acaba?
Evet, bilgisayarı
Bu aslında-
şarkı alsaydım ben bile.
Çok güzel ya. Hala aç bekle. Arada aç işte oyun oyna, kapatıp oyna. Kafa dinle.
Ama sen niye işten kaçırdın böyle bir şeyler? Herkes senin gibi işini layıkıyla yaptırıp kaçmaya aramıyor. Oradan çalışınca aile parayı vermek istiyor.
Bu müşteri hizmetlerine yardımcı olabiliriz. Telefonu kapat ve kafasını dönme.
Sen müşteri olarak
Adam şey konuşuyor ya.
maaş alıyorsun.
Her türlü harcama maaşını kardeşim.
İşte her türlü alacağım. İşi iyi yapmalısın ki
Güzel şimdi bir yerden gidiyorsan çıkıyor işte.
Hemen
Hayır hayır. Zaten birbirine tanımaz.
Onu hemen düzelteyim sonra görüyorum.
Yaptınız mı abi siz? Yapalım çok kolay da yapamadım mı?
yapamadım abi.
Ben DPT'yi yazdım onu söyle.
Uğraşmadım.
Yapıyoruz.
Bir yapsan bir baksan da
Hangi?
Hocam ben de senin numaralarını öğrendim. Sen ne bir de senin yanlış başlayacağım. Böyle yapıyorsun.
Yeterince öğretmiyor. Numarayı da yazmasam olur mu Serpil? Benim numaramı da bulursan sen kendin.
Şuraya eksik yapmam.
Bulurum.
Son kararda.
Ben de iyi insanlar. Kaç para vereceğim bana yapan karşılığında?
Bunların içine çıkartıyorsun ya parayı.
Bunlar öyle başlıyor.
Canlı bandı beğenir de.
Evlilikler gidiyorum.
Burada 2-3 mi yaptın? Onu da şey.
Burası normal.
Ya bunlar işleri yaptı ya.
Yani hoca burada eksi 3'lü yapmış. Eksi 3'lü yaptığı için bizim bu şeyden çalmak.
2-3 mü? 2 ise geleceğim.
Geçmiş şey kaç sene.
Benim doküman hayatım kaçmış.
Hepsinin kaydısı aynı zaten. Ama burada 2 tane
Ne yazacağım ben?
2 tane.
Ben silah mı?
İşte bize en son bakacağım.
Sen sistem ismi yazdın.
Şuraya gel. Şöyle oturup buraya gel böyle otur.
Böyle olunca ne oluyor? Gidiyor mu?
Senin çok garip bir not almışlık var ya. Ha. Yani konu öyle konu başlığı şey değil ya. Şunu bile çiziyorsun mesela. Bana lan. Bana var oğlum. Ne iş var ya? Bu arada niye bizi çekiyorsun? Direkt ben bunu evime çekiyorum. Direkt bizi çekiyorum.
Yemeden normal tarzı da öyle.
Oğlum sıcaktım, sen niye bunu çıkardın? Tişört var mı? Bunu çıkaralım.
Konuya bakacağız ya.
Hayır, konu o değil. Konu icazetse sıfır da gidebiliriz. O benim için sıfır o. Buna da gezebilirim. İcazet. Yani namaz bile kabul oluyor. Yani Hamza da seviyorum Yoksa millet dışında 4 kişi olduk ya. Şuradan gömlek giyiyor. Yani bana kalsa ben tek olsam. Ben sıcağa hiç gelemiyorum. Sıfır bak tam kamyon devreye gidiyor. Böyle kamyoncu atıyor.
Allah.
Bir de Şenol Kompüteşim. Kendine geç kazarsa gücü o. Hastalarını bilmiyorum da. Kim bu hastaneydi? Yakup Hocam hastaneydi. Tabii ki. Hatta çok garip bir şey var. Ben hastanın ders alamadım.
Bakarız belki.
O hastana benzer bir daha var. Acaba kardeşim bilmiyorum da. Ona bakmadım işte. Ben de o yüzden hiç sormadım. Benden de. Ya niye yapıyor adam? 10 dakika geç kalmış.
Onu biraz motive etmemiz gerekiyor.
Oğlum oradan mı başladın, buradan mı başladın? Gel mesela geldim buraya oturdun, tamam mı? Yani zaten geldiğin çoktan masadaydık ya. Geç gel.
Böyle İki defa mailime cevap verdim. Ve direkt cevap verdim. Yapılması için ama yarım saat dedi ya. İşte 5 dakika falan konuştuk ben. Önüne geliyor. 10 dakikası demo yaptım.
Depoya gitsin. Eksik olanlar için. Anladım, bu konu güzel. Bu konu diğer konularla çok bağlantılı.
Birkaç tane fake kullanacağım. Boardlar için bir board var.
Chapter 4
Bir tane fake boardlar için hepsi. Bir tane fake de işte böyle oynak sevgili falan.
İçinde bir sürü şey var. Gençleri kullanıyor.
Bir de video kontrol etmek için board linklerin direkt kopyaları bu şeyden geliyor. Aslında karıştırıyor ama
İyi olmamış, 50'sini şey yazmamış. Üstüne gidelim. Üstüne gidiyor, o bilgileri kullanıyor. Ben yapıyorum. Mesela şeyi sordum, niye
biraz daha arkadaşlar direkt şey yapabilirim.
öyle de bunu olacak. Yoksa yeni bir şey kalmadı hiç. Bir de bunun çoğu yoktu ya. Oğlum şu an çizdiği şu bile yok ya. 5 bilgisayarda falan olacak. Şu an yeni bilgisayarda yok zaten. Tamamen kapalı. Kaçta gideceğiz? Sistemin üstüne işte. Bir şey yok. Gel hadi onlar. Biraz millet erkek görüyor. Başka yerden versin. Geçen yıl öyle. Geçen de koruyor. Yüz yüze olmasını istiyoruz. Sistem zaten proje açmış, onu açmıyor. Sistemci açmayacağım demişsin. Bir yer lazım. Ama işte olmadı, onu nereden alacağız? Marmara'ya ben kabul ettiğim ama şöyle, 900 lira değil bizimki, ikinci dersi
Okay, so let's talk about this 63 average. If you have only 25 sectors per track, this is the picture. Okay, 25 sectors per track. This is sector number 0, 1, and this is 24. And as you see, the length of the sector is different at the outer end, okay, than the inner end. But usually we keep the same number of bytes. It's like 512 bytes per sector, okay. But when you get very very dense, keeping this kind of a picture becomes difficult. So this is what you do, okay. So at the outer tracks, I keep 32 sectors, okay, and at the inner track I keep 16 sectors, okay. This is sector number 16. So I cannot. So with this picture I cannot say how many sectors per track. Well, on the average here it is 32 plus 16 over 2, right? On the average it is like 24. But not exactly 24. It is 24. So I can change this. If we have many more tracks like this one. How many tracks do I have? Tracks per. Okay. Number of cylinders is this many. Okay. So many cylinders. 36,000 cylinders. Very very big number. Okay. Good. By the way. Our file systems usually, device-independent file systems usually, they assume this kind of a structure from our desks, okay? They think that I will give the track number and the sector number on that track number, and that's the thing. Okay, so it is the task of the device controller and device driver to show a picture to the file system. So logically, although underneath the hardware is implemented this way, but virtually I show it myself. I show the upper level myself like this. It's a more uniform way of showing it. That device driver becomes more difficult. That control becomes more difficult to implement. But on top of it, everything is more uniform. Okay, so the disks are part of our life, computer systems life, mechanical disks. We like them. We like them because they are reliable. Okay, we know how they work. They have problems, but we found solutions to those problems. One thing that we cannot solve, kind of, is this mechanical stuff, this rotation time. Well, it is fast nowadays. Instead of rotating like 5 times a second, nowadays we are rotating 15 times per minute, 15,000 times per minute. It is a lot faster, but you are not going to go faster than that. Okay, there is a physical limit. If you try to, if your outer ends of your platter reaches the speed of the sound, if you are more than the speed of the sound, that will create lots of other problems. So I cannot push that boundary. There are physical limits. I can't do more than that. So what are we gonna do? Are we gonna stop? No. Some people said that why don't we maybe I should show you this one. Why don't we run 8 disks at the same time? Okay, for each byte, keep the bit number 1 in the first disk and the bit number 1 in the second, third, fourth, fifth, etc. Right? So instead of using a single disk, I am using 8 disks or 7 disks, and I am dividing my data into these 7 disks bit by bit. So that means what? My read speed becomes 8 times or 7 times faster because I have distributed my data. I have distributed my data like that. Okay, so it is 8 times faster in terms of read, 8 times faster in terms of write. Okay, that's good, right? I mean, since disks are getting cheaper and cheaper, I can deal with this kind of a picture now. Okay, the thing is that mechanical drives, since they are mechanical, they are prone to mechanical failures. So I have increased my chances of getting a mechanical failure. So, I mean, if this one has 10,000 hours of expected lifetime, that means what? For a given hour, there is a 1 over 10,000. There is a 1 over 10,000 chance that it's going to fail. So now I have to multiply that chance by 8, because there is 8 times more chances of getting a failure out of this. So they say that, well, we can solve that problem. Do the same thing. Instead of keeping your data, if you're keeping your data in 8 disks, let's keep your data in 16 disks. The second set is exactly the same as the first set. Okay, so I can keep copies of the same data in another disk. So it is both kind of taking a backup of your stuff. Also, your reads and writes will be much faster. This technique is called RAID. Okay, redundant array of inexpensive disks. Okay, we are not saying that use the latest state of the art disks together. Just use the average disks together. Okay, 8 of them, 16 of them together. And that way, if you are careful about your data organization, things will faster in terms of writing and reading. And if you keep enough spare data, if you keep enough redundant data, okay, then your data will be reliable too, because you will become more tolerant to crashes. Okay, more tolerant to crashes. Usually this is what happens. Okay, this is what did I say? I'm going to, yeah. Let's look at this picture. This one says that, let's say our word is just 4 bits. I have 4 bits distributed, so this is 4 times the read and write speed. Okay, this is good. And I have a parity disk. There is a parity disk. What is parity? It's just, if my data is 1 0 1 0, you just keep okay, if you have even number of ones, like I have 2 ones, right? This is 1. If I have 1 1 1 0, odd number of ones, this is 0. Okay, that's called parity. You already knew this from some other courses, I guess. Okay, so this is a parity disk. I'm keeping the parity. While I'm running this, if there is a crash, let's say this disk has crashed. Okay, what am I gonna do? I detect that there is a crash. I counted this 1 0 0, but this one says 1, so it has to be 1, right? And in this says that 1 1 0. This one says 0. Okay, this one has to be 1 now because of the parity. So I can recover single drive crashes immediately. Okay, so replace this drive, put another drive, put your data back in, and continue. Okay, so I made things more robust. Also, I am 4 times faster. Okay, well, you have to spend 5 times more money, but it is better than trying to find a drive that is very much faster than what we have, and in fact we don't have those kind of single drives. So those drives are called single large expensive disk. Instead of using single large expensive disk, if such a thing exists, we use redundant array of inexpensive disks. Okay, so idea of parallelization. Of course, I mean, these are just the pictures. Things are not as simple as they look. There are many problems. Let's look at the types of the RAID structure. As you see, there are different levels: level 0, level 1, level 2, and level 3. Don't let the term level confuse you. Level doesn't mean that level 0 is worse than level 1. Level means it's just a class. RAID class 0, RAID class 1, and RAID class 2. So some of them have advantages, some of them have disadvantages. Level doesn't mean that level number 8 is okay, or level number 6 is much better than the others. Okay, again, they have their advantages and disadvantages. So at the beginning we have level number 0, class number 0. Instead of dividing our data bit by bit, okay, we divide them strip by strip. Strip means collection of sectors. Okay, let's say given a track, okay, we have many sectors, right? Okay, so we say that this is my strip number 1, strip number 0, 3 of them, another 3. This is strip number 0, strip number 1, strip number 2, and strip number 3. So I put k sectors in a strip, and I distribute them like this. Okay, strip 0 goes to this place, strip 1 goes to this disk, and 2 is here, and 3 is there. So I distributed my sectors evenly between these disks. Okay, the problem, I mean, this is a much simpler organization bit by bit. Okay, because whenever you read or write a single byte, I distribute them between the disk, but this one requires very careful synchronization between the disks. Okay, they have to rotate at the same time. Their disk heads and rotation angles have to be very carefully synchronized. Otherwise, I cannot read the same byte from all of them. If you like to avoid this kind of bit-based organization, bit-based synchronization between your disk drives, then you do this strip-based synchronization, which is much simpler. Okay, The problem with this approach though, what is the problem? If you keep reading the same sectors, okay, from strip 0, then you are just using this hard disk, not the others, right? So parallelization may not be that efficient, as efficient as this one. So if you keep reading around the same data, if you keep reading from strip 0, strip 4, and strip 8, you are not using your parallelized structure. Your speed is same as the single disk. Okay, so this one doesn't need any synchronization. Well, it needs synchronization, but not as careful as this one. But there might be some issues with the parallelization. Okay, good. So this is level 0, and level 0 has problems with application that has data sector by sector. Okay, when you do this, give me a sector number 0. Okay, here it is. This, then 1, then 2, then 3, then 4, then 5. So I mean, there is nothing parallel in this. You keep reading this one first, then this one next, then this one, then that one, then come to back. So parallelization is an issue with this level 0. Some people said that also this has problems with the problems about the data crashes, the hard drive crashes. If one of the hard drives crashed, then the whole data is gone, right? I mean, you might say that I had the strip 0 and strip 1, but most of your data will be gone. That's not a good thing. So they say that, why don't we use this? This is good both for parallelization, also the security of your data. Why? Because if you read sector number 0 and 1, you read your sector number 0 from here and sector 1 from there, right? So I can, since I have 2 copies of the same thing, okay, these are the copies. If the disk is shaded, these are the copies. I can read the sector number 1 from here, sector number 2 from there. Okay, so well, I mean, if I am reading the whole file, of course I can read it in an 8 times the speed, because I have 8 disks now. I can be as fast as 8 times faster. Also, in the worst case, if I am doing it like sector by sector, I can make it faster. Also, if there is a crash, let's say this one has crashed, let's copy all of them to the new drive. Okay. And if you don't like this stripping structure, okay, we can switch to the speed structure. And again, this is always 8 times faster in terms of writes and reads, but this is kind of vulnerable to crashes. If one of your drives go, okay, then you are dead. For that, I can use this level number 3. Okay, there is a Parity Disk. It's always running. So this is the level number 3. So level 0 has reliability problems. Level 1 is more reliable. Reads are faster. Reads are faster, but writes are not, right? I mean, for this one, you need to write it twice. So writes are the same speed as before, but reads are faster for this one. Okay. Then level 2 and 3 do not use strips. They require all drives to be rotationally synchronized. Level 2 uses Hamming coding for error correction, but I'm going to show you this level number 3 for the well, I mean, you might say that this one has a problem in terms of data recovery, but if your device driver, RAID driver, when you give it 16 bits, okay, 16 bits of data, write it to this structure, it just translates the 16 bit into 24 bits using this Hamming coding, okay. So instead of writing 16 bits, I am writing 24 bits, okay, to this structure. So I am using more data, but I am building in some redundancy. That way, if one of the drives crash, then I can recover my data from that. Okay, so Reliability, robustness comes at the expense of using more disk space, but these, as the name says, the disks are redundant. They are cheap. I can use many of them. Okay, instead of using the Hamming correction, I use the parity correction at the level number 3, and then we have other stuff like this. Again, stripping. Instead of using the spits again, use the same idea with the stripping. Parities are here, and some people say that it's not a good idea to keep your parities in the same disk when you do the stripping. Okay, when you do the strip, if you keep your parities on the same disk, if the things are always good, I am wasting this disk. I am not using this at all, right? I cannot make my data 5 times faster because I have 5 disks. It could be at most 4 times faster because this doesn't have any useful data if the things are good. Okay, so this is the case then. Why don't we distribute these parity strips over the 5 disks? That way you can read strip 0, 1, 2, 3, and 7 at the same time. So sometimes it is 5 times faster. And with the level number 7, it's a different configuration. I do it this way. Okay, so I gave you this 6 different types of RAID levels, and it looks like you can make up your RAID structure too. It is not that difficult to come up with a new idea, but the main idea is basically redundant array of inexpensive disks. Okay, you have many disks, they are cheap. Okay, their rotation times, their seek times are around the state-of-the-art numbers, but they are not the best of the world. But I can again see this one. If I had the RAID technology in 1984, okay, if I had the RAID technology by 1894, if I connected 8 of them together or 10 of them together, okay, 10 of them together, my transfer rates would have been 2.2 milliseconds per sector, right? So 10 times faster than what IBM offers during those days. That would have been an impossible number even for the most expensive disk. Okay, that's the case for the mechanical stuff. And the idea is nice. Remember our memory hierarchy. At the top we have the registers, then we have the cache, we have the main memory, then we have the secondary storage. Always the data, the location, the medium is getting larger and slower. So this is slow and this is fast. Also this is large, this is small, right? Okay, so we are getting larger and smaller. So whatever the technology here is, it is, whether it's a disk or a solid state drive or tape drive, doesn't matter. It can use this RAID technology. Okay, RAID technology says that, okay, use many of them because they are cheaper than your main memory, right? Use many of them and parallelize them. Okay, we can always do this. So building a RAID using the SSD technology is possible too. Good. Any questions about the RAID technology? Our modern operating systems, they support this RAID technology. You connect 5, 6, 7 whatever hard drives to your computer, and you tell the Windows operating system that you like to build a RAID system out of the 6, okay, using level number 2, 3, 4, whatever it is, and it does it for you automatically. Okay, and you can test it. Good. Okay, so if there are no questions, let me continue then. Let's talk about disk formatting. Okay. Disk formatting, again, this is our disk and these are our tracks. Our tracks are divided into our sectors. Okay, this is just one sector, right? Just a single sector. Okay, remember in 1984 this sector used to be, there are 9 sectors in a single track. In 2010 there are 60 sectors in a single track. Doesn't matter, it's a sector, and usually we keep 512 bytes on a sector. That's what we do. Okay, so this is a sector. But how do I keep this sector on the disk is a formatting issue. This is how I do it. This is just a single disk sector. I keep 512 bytes in this data field of the sector. Before the sector data starts, there is preamble information. Okay. When you receive your hard drive from the manufacturer, when you receive your hard drive from the manufacturer, there is nothing on your hard drive. It is not formatted. There is no data. So your hard drive starts formatting your disk. First, it writes this information. Okay, it says that this is the beginning of the sector. I will have first this the preamble part, and my data in the second part, my data, and at the end I have something else. Okay, so I need to write this data first to the disk. It's called low-level formatting. Low-level formatting it puts this structure on my disk. So on each track it puts this information, preamble, data, and of course the data is nonsense. At the beginning there is no data, but preamble and ECC is something meaningful. Okay, preamble starts with certain bit pattern that allows the hardware to recognize the start of a sector. Okay, so it has some certain bit pattern. Whenever the read-write head reads that data, it just knows that there is a sector starting. Okay, after that special pattern, I have more information, such as the cylinder number of that sector, okay, and the sector number of that sector, and some other information. Okay, by reading this preamble, you know what cylinder you are at and what sector you are at. Okay, now the hardware knows. This ECC is for checksum. It is the data, okay? It is the data about this data. You calculate this ECC number by reading this data. Calculate it like a hash code, you may call it. Calculate this number, ECC number from this data. If the number that you have calculated is the same as ECC, then your data is valid. Otherwise, there is a problem with this sector. Okay? If the number that you have calculated from the data is different from ECC, then you are in trouble. Maybe this sector is a bad sector. I don't know why it is bad. Maybe it's a mechanical problem. Maybe it is a surface problem. Usually it's a surface problem. There is a problem with the surface. Okay? So it has to be marked as a bad sector, and you mark it as a bad sector at the preamble section. You will say that this sector will not be used because it is bad. I am not getting whatever I am writing to there, okay? In the low level formatting, you do this. You write your preamble, you write some random data, and corresponding ECC is written there. And after you write it, you read it back to see if you are getting the same thing. If you are getting the same thing, you are fine. Otherwise, you write it again and try it many times. If it doesn't work, then you give up and you say that, although this is a brand new disk, okay, I am marking this sector as a bad sector. Okay, I am marking this as a bad sector because this is not usable. I am not getting whatever I am writing to there. So this is called low-level formatting. Okay, low-level formatting. As you see, I didn't talk about any inodes, file access tables, superblocks, and etc. Low-level formatting is lower than that. Okay, it just marks the sectors of each track one by one for all the cylinders, for all the tracks. That's why it takes a little bit longer time. If you try to format a disk, let's see if I can. I don't want to do this, but just do okay. Can I? How do I format it? Maybe the features. Go to the features and maybe from the.
Hocam sağ tıkladığınızda biçimlendir var.
Where was it?
Right click and biçimlendir.
Yeah, this is formatting. When I click on this one, okay, it's just an information for me to you are doing something crazy. Can I? Maybe I should insert a USB. Can I? Well, I mean, it's going to give you. I have a USB. Well, it is not. I don't have a USB port. Well, it will tell you. It will tell you. Should I low level format it, or should I format it in a fast way? Fast formatting is this. Don't do low level format. Okay. Just put a new file system on it. Okay. New file system means that for the inode based file system, dealing with your super nodes, your inodes and everything. So you don't touch most of your data on the disk. You just invalidate everything. You say that there is no data on this disk. I am just putting a new inodes. Or FAT based system, you just say that I don't have any data available on this disk, and that's it. So fast formatting doesn't do any low level format. But if you do the low level format, you have to go to your tracks one by one and write this information. So that's why it takes longer. Okay, good. So this is disk formatting. Okay, any questions so far? Again, you might say, why are we talking about this mechanical disk? I did not see mechanical disk for the last 5 years. All the computers are being sold are with the SSDs, especially the portable ones, because SSDs they don't have spinning parts, so they are not prone to mechanical failures. Okay, and they are faster. They are kind of more reliable, but still our mechanical disks are larger, and for our network servers, file servers, and those kind of large computers, we use mechanical disks a lot. Okay, that's why they are kind of relevant. And remember the rule. We keep solving the same problem over and over again, because whenever a new type of less powerful computer type appears, cheaper, less powerful, they tend to use these kind of older technologies first. Okay. Another issue with the disk formatting is, again, this mechanical problems. This disk rotates very, very fast, maybe 10,000 times per minute. Okay, 10,000 times per minute. So it is spinning very, very fast compared to our read-write head movement. Let's say moving. This is my read-write head, or more technically. Okay, this is our read-write head. It is moving this part. Okay, it's reading it. To move this head from this location to this location, okay, it is the seek time. It takes 6 milliseconds. What was the for the Western Digital one? On the average, it used to be 0.7 milliseconds. Okay, it's going to take 0.6 milliseconds. Okay, 0.6 milliseconds is a lot of time. By the time I moved my head from this location to this location, okay, this disk is spinned a lot. So I cannot go directly from this sector to this sector. At most I can do is I can move this location to this location. While I am doing this, the disk is rotating. Instead of accessing the sector number 29, probably I will access the sector number 2 because disk has rotated, right? Okay, so that's a problem. What am I going to do? I cannot access it in the way I wanted. So they have introduced this cylinder skew idea. Okay, cylinder skew idea, and I think I'm going to talk about it. I am going to talk about it tomorrow because I don't have time right now. But basically, okay, this is what you do. Okay, you don't number your sectors by the same. You don't say this is sector number 0 of this track and 0, 0, 0. You do it this way. 0 is here, 0 is here, 0 is here, 0 is here, and 0 is here. So there is a skew amount. Skew amount is 1, 2, 3 sectors. So my sector structure is skewed by 3, and this is called the skew factor for your disk. Okay, so this is called cylinder skew, and this is, by the way, I do this when I do the disk formatting. Why? Because in my preamble I said this is sector number 0 or 1 or 2. Okay, so when you are doing the low level formatting, you indicate your skew amount and you put that number in here. So the skew amount is not set by the factory, it is set by the low level formatting. Okay, any questions? Okay, that's it then for today. On Monday, as I said before, we have a guest speaker. Mustafa will talk about virtualization and containerization. I will take my regular attendance. Okay, see you on Monday. Sen mi imza atmamıştın? Gel.